All right, hello. Excuse me, and welcome to my review video for the homework response questions for spring break. I'm going to walk through each of the parts. You should score yourself as I indicate and make corrections. And then be sure you read the scoring guides and fill out the score report. So let's take a look at the first one. Both of these are non-calculator questions. Remember, they're trying to rope in problems that have to do with the MVT or IVT or EVT, and then flex some other kinds of calculus skills as well to keep those things fresh in your mind, okay? So let's see, train A runs back and forth on an east-west section of railroad track. So we have a train running back and forth east-west here. I don't know, maybe doing this kind of thing, right? East-west on a railroad track. The train's velocity, we're looking at velocity, is measured in meters per minute, is given by a differentiable function, v sub a of t, where t is measured in minutes. Selected values of v sub a of t are given in the table here. Find the average acceleration of the train on the interval 2 to 8. So we got some hints in here. We want something about acceleration. We are given velocity. Acceleration is the rate of change, right? The rate of change of velocity. Acceleration is the rate of change of velocity. So we're going to need something to do with the slope or derivative, right? Okay. So the average rate of change of velocity, this sounds like an average rate of change. That's the slope of a secant line. So I need v sub a of 8 minus v sub a of 2 over 8 minus 2. Let's see, v sub a of 8 is negative 120 minus v sub a of 2 is 100 over 8 minus 2 is 6. So this is going to give us negative 100 and negative 220, my bad. Negative 220 divided by 6, which will give us negative 110 divided by 3. Looking at, this is an acceleration measurement, so it's going to be meters per minute, because the units for the numbers in the numerator were meters per minute. The units for the denominator were minutes, so it's meters per minute, or meters per minute squared. Acceleration. Now you may go, well, average acceleration, don't I use my 1 over b minus a integral formula? Remember, the integral formula is if we're trying to find the average of the function or the thing that we're looking at there, if we already have that function. So average acceleration, I could have also found 1 over b minus a of the integral from a to b, which is 2 to 8, of a sub a of t. Yes, you could have done it that way if we had a sub a, the acceleration function, but we don't have that. So we have to approach our average acceleration by taking the average rate of change, the slope. We're trying the average derivative thing, right? So that's the difference. We would use the integral formula if we actually had the function for acceleration, but we don't. Okay. So this one was only 1 point. It's 1 point for the average acceleration, which is over here, negative 110 over 3. Okay. Let's take a look at part B. Part B says, do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some point? Is it negative 100 meters per minute at some point from 5 to 8? So let's take a look. We want to know, is the velocity going to be negative 100 somewhere between 5 and 8, non-inclusive? 5 and 8. Well, just looking at velocity at 5 and velocity at 8, our velocity started at 40. It ended at negative 120. So if our velocity is continuous, then yes, our velocity would have to have been negative 100 meters per minute at some point to go from positive 40 to negative 120. Is our velocity function continuous? It is, because we know that the velocity function is differentiable. So there's our key here. So we need to say v sub a is continuous. We can even go farther, and I would encourage you to do this and say v sub a is continuous because v sub a is differentiable. There we go. So now we have established what we need to be able to use. This would be an IVT thing, because we need to prove that we are passing through some value on a function we already have. Okay, so what do I need to show now? I need to show, okay, v sub a of 5 is 40 meters per minute. V sub a of 8 is negative 120 meters per minute. And then I could say 40, or I can even make another kind of expression. V sub a of 5 equals 40, which is greater than negative 100, which is greater than negative 120, which we know is V sub a of 8. Otherwise, we could say, hey, V sub a is continuous because V sub a is differentiable. We know V sub a of 5 is 40, V sub a of 8 is negative 120. Therefore, by the intermediate value theorem, by the IVT, there is a time t on 5 is less than t is less than 8, such that V sub a of t is negative 100. Now, you don't actually have to write things out like I did in this line, but this can be useful just to show the reader that I know, hey, starting at 40, that's bigger than negative 100, that's bigger than negative 120, that's where I'm ending. Therefore, by the IVT, there's a time where this is going to happen, that velocity is going to be negative 100. You don't actually have to say that, but at a minimum, you need to show and indicate that V sub a of 5 is greater than this V sub a of 8. You have to state that somewhere. So you can say it in words, V sub a of 5 is greater than V sub a of 8. And we have to state that negative 100 lies between those values. So you could also have indicated things that way. Lies between those values, and then say, therefore, by the IVT, there's a time t from 5 to 8, such that V sub a of t is negative 100. So point-wise here, you got 1 point for stating either this line here or similar conclusion in words, and then 1 point for your conclusion using the IVT. All right. As part of that, you have to have this stated, but you need to at least for 1 point state this, and for another point state this conclusion with IVT. That continuity part has to be there. All right. Let's take a look now at the next true response question, a little more challenging one. I'm going to kind of bounce around since we got kind of a bigger problem to work with here, okay? So we have a table, and it says the height of a tree at time t is given by a twice differentiable function, h, where h of t is measured in meters, and t is measured in years. Selected values of h of t are given in the table above. We know it's a twice differentiable function. We know h is measured in meters, is measuring the height of the tree. So it says use the data in the table to estimate h prime of 6. Using correct units, interpret the meaning of h prime of 6 in the context of the problem. Use the data in the table to approximate h prime of 6. Well, here's the deal, right? H prime, that's talking about a derivative. We're talking about a derivative. H prime of 6 would be the derivative right here between these two numbers. We don't actually have information to be able to do that, so we have to just estimate it by using the slope, slope made from the surrounding 2 points, the slope of the secant line. So we can say then that we can do h, what would be good? H of 7 minus h of 5 over 7 minus 5, which will give us h of 7 is 11 minus h of 5 is 6. If you, so 11 and 6, sorry. And the units there, we'll go ahead and put those on so they indicate we need units as well. 11 minus 6 meters over 7 minus 5 is 2 years. So that'll give us 5/2 meters per year. So that works. So there, we use the data to estimate the derivative. That's 1 point for getting this estimation here, 5/2. Now we need to interpret the meaning of the derivative. This is where on the benchmark we had some trouble, so we got to be really specific here. When we're writing about interpreting the meaning of the derivative, we got to say h prime of 6 is the rate of change of height, of the tree, because the derivative will be the actual rate of change, right? So it is the rate of change of height of the tree. Then we got to specify units in meters per year. And we got to specify the time at t equals 6 years. Notice I'm interpreting the meaning of the derivative, which I didn't actually find, but if I did find this, using correct units to interpret the meaning of this derivative in the context of the problem, that derivative would be the rate of change of height of the tree in meters per year at t equals 6 years. Getting the units, getting the time we're evaluating it at, and its units as well. So this would be 1 point for 5/2 and 1 point for this explanation here with units. All right, let's take a look at part B. B, explain why there must be at least one time, 2 to 10 non-inclusive, such that h prime of t is 2. So we have some cues here, right? We've talked about before. We're given an interval. We're also given a question about a derivative of the thing we have. We're given a derivative question on some interval, and that derivative is not a function we're actually given. So this should cue us then to think, hey, this is an MVT question, because the MVT talks to us about the derivative, the rates of change of stuff on some interval. So for MVT, for part B, for MVT, we need to be able to specify and state that the function is differentiable. So we can say, is h differentiable? H is actually twice differentiable. So I can say then h of t is differentiable. So I have to state that differentiable and continuous. Differentiability implies continuity though, but we should write out h of t is differentiable and continuous. Then, if that's true, now I can find my average rate of change. I can find the slope of the secant line across 2 to 10. So that means I need to find h of 10 minus h of 2 over 10 minus 2. What is that going to be equal to? H of 10 is 15. H of 2 is 1.5. 10 minus 2 is 8. 10 minus 2 is 8, right? So, wait a minute. I made a mistake, didn't I? Well, no, we didn't. We got to just think through here. So this, we got to be careful about. So I almost fell into a trap here, because this interval here, 2 to 10, this won't give us a derivative 2, won't it? This will give us what, 13.5 over 8, right? Got ahead of myself there. I'm sorry. This will give us 13.5 over 8. That doesn't actually tell us very much yet, does it? Well, let's see. We're looking at this whole interval. So if we can prove that there's at least one of these intervals where the derivative is 2, then we should be able to conclude that there's got to be at least one place from 2 to 10 where the derivative is 2. So is there one of these intervals that will give us an interval of a rate of change of 2? Well, 2 to 10 didn't actually work. Let's try a different interval. 2 to 3, just looking at my y values, that's not going to work. 3 to 5 might work, so let me try that. So let me try h of 5 minus h of 3 over 5 minus 3. See, h of 5 is 6 minus 3 is, h of 3 is 2 over 5 minus 3. is 2. So that's 4 divided by 2. That'll give us 2. Okay, great. So what did you just figure out? We found out that the average rate of change here from t equals 3 to t equals 5, that does give us a slope of 2. So what can we conclude? This is where we go to our MVT. We know this function is differentiable. We just found an interval where the average rate of change was 2. The slope of the secant line was 2. So we can conclude there's got to be a place where the derivative is 2 as well. Notice we started by looking at the sort of the full interval, but it wasn't useful for us. So I started to look at the subintervals and found one that did work. So we can make our conclusion then. I'm going to go ahead. This is going to seem a little funny. I'm going to move the conclusion down here. I'm going to add something up here. H of t is differentiable and continuous on the interval. Let's do the whole interval then. 2 to 10, just to clarify to them we understand that. Okay, so we know h of t is continuous and differentiable in 2 to 10. We found an interval where the average rate of change is 2, so we can conclude, therefore, by the MVT, there exists... Ooh, spelled that wrong. There exists a value, I'll give it a name, a value C on 2 is less than C is less than 10, such that h prime of C equals 2. And then we have all our parts. We stated continuous and differentiable on our interval. We found a interval on that larger interval where the average rate change is 2. Therefore, by the MVT, there exists a value C on the interval 2 to 10 such that h prime of C is 2. All right. This one was 2 points. One for getting your average rate of change, the one that worked over here, this h of 5 minus h of 3 over 5 minus 3. And then 1 point for your conclusion using the mean value theorem. Remember, you have to state that things are differentiable and continuous. All right. Okay. C, use the trapezoidal sum with 4 subintervals indicated by the data in the table to approximate the average height of the tree over the time interval 2 to 10. Okay. The table measures height, right? So this is where average height, I have something that measures the height. I want the average height of it. So this is going to be my integral formula. So this is going to be 1 over b minus a. So that's going to be 2 minus 10. There's my interval times the integral from 2 to 10 of h of t dt. Now, I don't have a way to actually evaluate this integral, but it says use a trapezoidal sum with 4 subintervals indicated by the data in the table to approximate this value. So I can do that. Remember, trapezoidal sum takes care of the integral. The trapezoidal sum approximates the integral. So the fraction in front is going to stay 1/8 times. And now I just have to get my trapezoidal approximation. So I'm going to go up to my table. This is a good reminder. Trapezoidal approximation. I'm going to leave this up here. That way I can just kind of write it in while looking at the table. Okay. Trapezoidal approximation. And my output values are down here. For trapezoidal approximation, I add together my output values for my first interval. So this is going to be like 1, interval 2, interval 3, interval 4. So my first interval, I add together my output values. This is the formula for trapezoidal approximation. Then I multiply by the delta t, which is 1, and then I divide it by 2. Always divide by 2. Plus, then I move to my next interval. Add together my output values, 2 plus 6. Multiply that quantity by my delta t, which is 2. 3 to 5 is 2. And then divide it by 2. Plus my next interval, add together my output values, 6 plus 11, that quantity, times the delta t, which is 5 to 7, that's still 2, over 2. Plus, add together my output values, 11 plus 15. 11 plus 15 times my delta t, which is 3 in this case. We always multiply by your delta x, delta t. How far over are you moving, which is 3 in this case, and then divide by 2. As a reminder, our general formula, we add together the y1 plus y2 times the change in the input value divided by 2, and so on each time. So this formula we're seeing here then should give us the trapezoidal approximation. Actually, should adjust this because this this is an approximation and not equal to. So let me adjust this symbol here. Get rid of those. All right. So what do we just find out? This thing over here, which would give us the average height of the tree, is going to be approximately, I kept the fraction in front, 1/8, times the trapezoidal approximations approximating the integral. And what's good about this is you don't actually have to simplify anything. You get 1 point for having your trapezoidal sum part of this, which is right here. All right, it's right here. And then you get 1 point for your approximation, which means including this 1/8 in front of it. If you have just both of these together, then you are all set. You don't need anything else. If you did simplify it all the way down, which I would not encourage you to do, you would get in the end here that this is going to be equal to 263 seconds. But please, please, please do not try to do that all by hand. Okay. 1 point for the trapezoidal sum, 1 point for including the 1/8 / approximation if you got all the way down to here, but please don't. All right, and last part, part D. All right, part D says the height of the tree in meters can also be modeled by this function g of t, or g of x. So I'm going to just write that down here. G of x is 100x over 1 plus x, where x is the diameter of the base of the tree. Make a note, x is diameter of base. So this is measuring the height as a function of the diameter of the base. When the tree is 50 meters tall, the diameter of the base of the tree is increasing. So we can say this, when the tree is 50 meters tall, so when g of x equals 50, just converting it to math language, the diameter of the base of the tree is increasing at a rate. We're given a rate. The diameter of the base of the tree. Well, the diameter of the base of the tree is x. And we just found out it's increasing at a rate of 0.03 meters per year. That sounds like a dx dt. The rate of change of the diameter of the base of the tree is 0.03 positive because the diameter is increasing meters per year. Okay, so when g of x is 50, dx dt is 0.03. That's the rate of change of the diameter of the tree. According to this model, what is the rate? Here's our question. What is the rate of change of height of the tree with respect to time at the time when the tree is 50 meters tall? So what do I want in the end? I actually want g, like dg dt, right? I want the rate of change of the height of the tree with respect to time. This starts sounding like a related rates kind of problem to me. Okay, so things are going to get interesting here. Let's go ahead and do this. We know then we want dg dt. So let's take the derivative of this. The derivative of g with respect to t will give us dg dt. We need the derivative over here, but this is going to be a quotient rule, right? This is going to be a quotient rule kind of situation is what's going to be interesting about it. Okay, so let's go ahead and do that. For a quotient rule, say to keep the low thing times the derivative of the high function. 100x will give us 100, but we just took the derivative of x, and everything is with respect to time. Everything's changing over time, right? So this 100 we took the derivative of x, so dx dt. So there we go. Low derivative of the high minus the high function times the derivative of the low, derivative of 1 is 0, derivative of x is dx dt, all over the low function, which is 1 plus x squared. Now, I want to figure out dg dt. I know dx dt, that's easy to plug in. I'm just missing x. So how do I figure out what x is? Well, I want to figure out this rate when the tree is 50 meters tall, right? In other words, I want to figure out what is the rate of change of g when g, the function I already have for the height of the function, when the tree is 50 meters tall. So what is it going to take to make this happen? Maybe you can do it by observation, or you can multiply and use your algebra. This will be 100x equals, I'm going to multiply 1 plus x to this side. That'll give me 50 plus 50x over there. Subtract 50 over here, that'll give me 50x equals 50. So x has to be 1, plug in 1, that'll make sense, right? So when x is 1. So I can go ahead and plug in everything I know. dg dt is going to be, well, when x is 1, that'll be 2 times 100 times 0.03 minus, when x is 1, that'll be 100 times 0.03 all over the quantity. 1 plus 1, that's 2 squared, that'll be 4. This, whatever that number will be the rate of change of height in meters per year. Now, you don't have to simplify. You can just leave things like that if you want. If you feel like crunching numbers down and things like that, that's fine. It turns out this one does simplify kind of nicely. We'd have 200 times 0.03 minus 100 times 0.03. So that'll give me 100 times 0.03 over 4 over 4. Well, 100 times 0.03, that'll move the decimal place 2 times. That'll give us 3/4 meters per year. And there we go. This would be the simplified form of it. What is the rate of change? It is 3/4 meters per year. Okay. Scoring-wise, you got 2 points for doing the derivative correctly, and then 1 point for your actual final answer. According to the model, the rate of change of the height of the tree with respect to time when the tree is 50 meters tall will be 3/4 meters per year. 1 point for this, 2 points for you doing it correctly. You could only max out 1 out of 3 points if you forgot to do the chain rule and you forgot your dx dt's in here. All right. Hopefully that helps you with these 2 questions. Be sure you check the scoring guide for some more clarity. Score yourself, make your corrections in different color, and submit the score report. Have a great break, everybody. After you're done with that, make sure that you then continue with the steps for this break, continuing on with the derivatives packet and the practice exam. Okay? Have a great day, everybody. Bye.